All right, everyone. Orbital parameters. Before we start, there is an exam on Wednesday. All exams will be in Pughall 170, so that you don't have to struggle with these terrible chairs here. That's a very big auditorium. You will have plenty of desk space. You don't have to be close to each other. Don't come late, because we are given 50 minutes. It's like a lecture time, so we need to be sitting down well before 3, so that you have the full 50 minutes. Because at 50, we're going. So whoever shows up late because they thought it was here, it's on them. I can't invent extra time, okay? So please be there before 3. If the lecture before us ends early, I'll be there like a quarter of 15 minutes ahead of time. So I'll be more than happy to give you 5-10 more minutes if we have them, but you need to be there, okay? What room is it? Pughall 170. It's far that way, I think. I had a class there at some point, but yeah, it's a nice place, better than this. Okay, so we are going to talk about orbital parameters today, definitely more than last time. Remember what we said, we defined a few quantities that are going to be an alternative to position and velocity in Cartesian coordinates. If this blue line is my orbital track, the intersection of its plane with the equatorial plane of ECI, of the basis fixed in ECI, which we have defined last time as the x-axis pointing at the gamma direction, z is the spin axis of the planet, and y completes a right-handed coordinate system. Well, so that intersection is defining the line of nodes, and we call the angle between the x direction and the portion of the line of nodes that sees the satellite going from south to north. We call that gamma, or right ascension of the ascending node. We call the angle between the specific angular momentum vector and the z direction the inclination vector. Inclination angle. We call the argument of perigee the angle between the line of nodes with the side with the ascending node and the eccentricity vector. And finally, we have the true anomaly, which we all know very well. So this P just indicates that this will be the perigee, because it's where the eccentricity is pointing. This is the Earth, and that's your spacecraft right there. And so we said a possible combination of orbital parameters that people use all the time is semi-major axis, size of the orbit, eccentricity, shape of the orbit. These three angles we have defined, which as I said, I will probably refresh other angles, but this is a 3-1-3 sequence, where the sequence of rotation will be, as we briefly mentioned, it will be basically big omega first, I, and then little omega, and finally the true anomaly. So these 6 quantities here will be your orbital parameters vector, if you want to call it that way, that are an alternative to the state vector, which we have called position and velocity. They are, in theory, more of a visual aid than R and V, of course, because, again, these 3 lock really the plane in place. They give the direction of the eccentricity vector. These pertain to the shape and size, and then that's your position. Now, I always try to justify why we do the things that we do, because we're going to today find a way to go from how you go from S to orbital parameters, and then we'll do vice versa next time probably. Why we use these orbital parameters? It's because once we will get to more elaborate models for this attraction acceleration, which means once we will start to add more things here, we will see that we can find differential equations of the first order in terms of these quantities here. Because with the ideal model that we have played with, H doesn't change, E doesn't change. The only quantity here that is evolving with time is the true anomaly. Everything else is frozen. The shape, the size of the orbit don't change, and its orientation in space don't change. But reality is different. Those things will be modified over time because of additional accelerations that we may start adding here when the time comes. Those are called the Gauss variational equations, so we'll cover those. And they are given in terms of these orbital parameters rather than state vector. Because it's much easier to visualize an entire plane changing orientation in space than looking at just a position and a velocity. Questions? Do we all agree that you want to refresh these when the time comes, probably next time, Euler angles? I don't know why. Euler angles is something that students supposedly see in multiple classes, but it's that one topic that they always want to see again. I don't know if it's just the way it's explained. It is not a trivial concept, but it's not that bad as people think. So they have some limitations. They have the singularity problem, but they're not terrible. So we'll do them, but not today. So how do I go from S to orbital parameters? That means I am given R and V. Sorry. So I have position and velocity at some given time. And I want to know A, E, I, big omega, little omega, through anomaly. I don't know what these are. So everything I'll do today is really just basic geometry, dot products, arc cosines, nothing more. So you start from R and V. Any ideas? You need to find 3 angles, actually 4 angles, and these 2 quantities here, same major axis and eccentricity. Any ideas? I'm going to write that one equation that I refuse to memorize, which is the following. The Laplace vector expression that leads to the eccentricity definition. So maybe this will give you a start. E is part of that. I need to find E as well. Except this is the vector and that's the magnitude, but once you have the vector, you're done. Okay, so I have V, I have R. What do you want to do? Angular momentum. That's the first step. So this is, if we have time, I'll show you, I'll start talking about uncollected homework 3 that does exactly this in MATLAB. But it's really an algorithm what you're looking at to solve for those quantities. So you start from H, which is R cross V, done. And that actually gives you E, right? Because that's the only quantity that is missing there. So imagine in MATLAB I've given you 3 quantities that compose the vector R, 3 quantities for V, cross the 2 vectors, you get E through that expression. If you want, I can just copy it here so that it looks like a reasonable sequence. V cross H minus mu R over R. And of course, E that I'm looking at is nothing more than the norm of this vector, just to be thorough. So 1 is done. Check. Okay. Now you should have enough information to play with the angles, right? What do you want to do next? Any of these is fair game. Which one do you want to do next? Inclination. How would you do that? H dotted with the unit vector of Z is equal to H cosine of inclination angle. Note Z as a magnitude of 1, so I don't even bother writing it on the right-hand side. Okay. Well then, the inclination angle is given by the inverse cosine. Do you prefer A cosine or cosine minus 1? Doesn't matter? No? Okay. Arc cosine of H. Oh, I can't write H. H dotted with Z over the norm of H.
Maybe negative 1 would be better, because A could be so interact.
I agree. That's what MATLAB does, right? No, the MATLAB uses the A. I think. How about this? Any corrections? You need to be careful when you use inverse trigonometric functions. You've seen them. You've seen these already in one of my MATLAB exercises that I was correcting an angle for certain cases that may arise, or for example that I was making sure that these inside MATLAB is always between -1 and 1, because slightly outside of that will give you a complex number. So this kind of care has to be, attention has to be paid every time you inverse a trigonometric function. So what kind of angle is this going to give you? What is the range of the result that you should expect when you do an arc cosine? What is the range of the arc cosine? Cosine of an angle is 1 as 0, is -1. This is basic stuff, right? At pi, and it does something like this, and this is pi over 2. So it's invertible where it's monotonic and it's 0 to pi, which means that that's the angle you're going to get. Whatever you give here to this function is going to be between 0 and pi. Yes?
Do we want it in radians or in degrees? Does not matter.
It doesn't matter. I think it depends on how you use it in practice. So I think there is an option to do arc cosine to give you directly a result in degrees in MATLAB. Then whatever it's produced, make sure that you use cosine d, cos d afterwards if you use it. You need to be careful about those things, because those are the usual mistakes that I make. I have something in degrees and I use it as if it were in radians, but it doesn't matter. But these usually, usually you see it, with this function you will see it in radians. So 0 to pi, is that okay? Is that an acceptable range? Do you want to do something about it? You want to change things? Now this is hard to visualize, but imagine what happens when you start from I equals 0. H is pointing as z, you have an equatorial orbit, and say it's the satellite is going around this way, so the H is pointing up. As you start moving H away from z, the opposite case is where H is pointing down, so you see the orbit run this way now. If I keep going, do I want to call I something above 180, or it doesn't matter? Basically, if I see H going down to 181, do I want to call it 181, or you think it's okay to do 179? I think you just do 179, because the motion is what matters. So imagine this orbit, you run this way, at 90 degrees, you go down, and then you keep going. You're basically going to be back at its equivalent to call it 179. I know it's hard to visualize unless you have a physical object, but what I'm basically getting at is that this is okay to just leave it as it is. Inclination, you will never see something outside of this in degrees. Once you get to 180, you just invert in the direction of motion. That's it. Okay, what's next? Or 0 to pi, okay? It's equivalent. I don't care. Which angle do you want to do next? You want to do the true anomaly? Okay. I was saving it for the last, but that's okay. Okay, how do you do that? You have R. I don't have it here, sorry. This is the position vector, right? And if you really want to be messing up the figure even more, you will have the velocity vector here pointing somewhere. Okay, so it's same. It's a dot product. How about R dotted with E is what? Is RE. Now these things do have a magnitude that is probably not 1 in general. Definitely not the radius. Cosine of true anomaly, which means the theta is the inverse cosine of the dot product of the two vectors divided by the product of their norms. Now, the way I think we have played with true anomaly, we said is 0 to 2 pi. So if we want to keep it that way, which I think is a good idea, you can do the following. You can do a little correction. If what? Because this is going to give you 0 to 180. The moment you pass 180, which is also called what? Don't tell me pi. I know it's also called pi. Apogee. So once you pass apogee, you're 181, 182. So we want to keep it that way. That's usually, that's what we've done. There's nothing wrong with calling it negative numbers, but that's usually what we do, 0 to 2 pi. So if you want to give an output that is 0 to 2 pi, what do you do? Because this is not going to give you 0 to 2 pi. It's going to stop at pi. And then the moment you pass pi, what is it going to do? It's just going to give you a positive number. It's going to give you 179, but from the other direction. That's probably not a good idea. Well then, I would say that if the radial velocity, the component that is radial of the velocity is negative, which means you're past apogee, look at the orbit from above. This is perigee, this is apogee, this is your planet, and the state vector is in the way. My unknown is in the way. I'll rewrite it. Okay, so terrible. Yeah, not too bad. So remember, you start from here, the velocity is perpendicular to position, then the radial velocity is positive. You're going away from the Earth in this first half. Then you get to the furthest point here, and the motion inverts itself. You're starting to get closer and closer, so the radial velocity is negative. By radial, I mean the following. I have the position vector, I have my velocity vector, and I project it along the radial direction, remember? So this is VR, right here. This vector here. And what did we call this? V perpendicular, right? So it's positive as you're going away, but the moment you start going back towards perigee, it's going to be negative. Agree? Okay, so if that's negative, well then I'm just going to say that theta is whatever this instruction gave me, correct it like this. So that will give me 0 to 2 pi. Do we remember what VR is? Because if you have to implement it, you have to check what this is. VR is this expression here, mu over h e sine of theta. So this would be the procedure. You have computed you compute this dot product, compute this arc cosine, check at that theta what's happening, and fix it. Okay, what else? So, okay, I have removed my unknown, which was done. Who wants to do this? This requires an intermediate step. The ran. We could do little omega first. No, we can't. I mean, it requires the same step. What is that step? V cross H? E cross H. I don't agree with that. The 3D view is misleading because you may have eccentricity that points. The eccentricity vector can point anywhere in this plane, so it is not necessarily, it is a 90 degrees with this guy, but it may just give you another line that is not n. It's almost that. H is there, which, so H is normal to the plane, and this line is the intersection between the orbital plane and the equatorial plane. And so if H is normal to the orbital plane, what is the axis that is normal to the equatorial plane? It's Z. So exactly what you're saying, but I'll just do it with Z. Make sense? Yep. So, so N, and let's call it, is this clear that this is a unit vector? I hope it is, because that's what I've used for unit vectors, the hat. it's z cross h, and then I have to normalize. Z cross h normalized by itself, of course. Agree? Z cross h, yeah, that gives you n. And so then I have x and n, and so I'm going to use them. So after this, what you're going to do is the same we've done so far. N dot x is, now these are unit vectors, cosine of big omega, capital omega, which means, I'm going to separate this somehow, which means another inverse cosine of simply n dot with x. And this also is usually defined as 0 to 2 pi. You can go around with the ascending node. And so I'm going to do this. If, let's see, because again, that arc cosine is going to only give me something between 0. 0 will be when the line of nodes is exactly the x-axis positive. So the ascending node, basically the satellite is crossing the equatorial plane south to north exactly on the x-axis, positive. And the other case at pi is when it's happening on the negative part of the x-axis. And past that is not going to make a difference. If I pass that point, this is still going to give me between 0 and pi. So if I want 0 to 2 pi, what am I going to check? I'm going to check that, for example, the dot product between n and the y direction is negative. If this is negative, then you do the usual 2 pi minus omega. I'm trying to write this in an algorithmic fashion, exactly how you would write it in a code, MATLAB. These are all operations you can do in MATLAB. The ifs as well. What is missing now? Now we can do little omega, for example.
Are we checking if n dot y is less than 0?
Is less than 0. Why?
Yeah, the y.
Why are we doing this?
No, why are we using y?
Because if the line of nodes is sitting, it's always sitting in the equatorial plane, of course, right? The xy plane. But if it's sitting in this quadrant here, x positive, y positive, that dot product is positive. If it passes y and is sitting in the quadrant of x negative and y positive, this dot product is still positive, and the angle is still at 180, below 180. The moment I pass, I don't want to mess this figure, the negative x-axis, and I keep going, is sitting in the quadrant which is, okay, so this is positive x, this is negative x, positive y, negative y. So the situation I have here is something like this. The line of nodes is right here, right? Then I keep going, keep going, keep going. Imagine that it's sitting somewhere in this quadrant. You know, the dot product between n and y is still positive, and the ran is still whatever the arc cosine is going to give me because it's 0 to 2 pi. But when I get here, I have passed the pi, which is this axis. And the dot product between n and y is negative. And so that's a trigger that tells me, okay, you passed 180. And the same if it's sitting here, it's still negative. You passed 180. And so if you want to give me a 0 to 2 pi type of solution, just correct that way. Make sense? Yep. That's it. Again, there's nothing wrong with going with different ranges. You can go 0 to pi and negative values, but you need to be careful to detect this, because if I don't do that, if I don't correct it that way, for example, again, my arc cosine is going to give me this angle, and I don't have a way, if I just use that number, I don't have a way to check if it's an angle counted this way, negative or positive. It's just giving me a number. Does that make sense? But you really need to know where that ascending node is. It's not enough to just get 150. And so if we just do it between 0 and 2 pi, and then it's univocal. You know exactly where you are. Okay, number 5 is little omega. Little omega, I have n now. I'm going to use eccentricity, and n, e dotted with n is e. N has magnitude 1, cosine of little omega, same story, little omega is an inverse cosine of E dotted with N normalized E. And there is some sort, I'm sorry about this thing getting a little extended on the side. There is another correction here, the same. If I want 0 to 2 pi, what do I check? The eccentricity vector can do anything. It can be sitting on the n direction. It can go all the way opposite to the other side, and it can keep going. So if I want 0 to 2 pi, I check that this is actually, what do I check? It's a similar dot product, but which direction would it be? So we're looking at this angle, right? From N to E, and you're moving in the orbital plane. So E can start from here to from 0, can go all the way around, it can go to pi, which is the opposite of N, and then it can keep going, it can go down, basically in the semi-volume below the equatorial plane. How do I check if that's happening? What's a good way? I know that figure says a lot of stuff, but basically, if you have a 3D representation of a vector x, y, and z, this is the vector you're looking at, right? E. How do you check if E is above the xy plane or below the xy plane? Z, the z component, that's it. So it's basically E dot with z, right? If E dot z is negative, same story. I'm going to fix that angle like this. Done. Okay, the way I've chosen the orbital parameters has A, some people actually have H. So some people will be done at this point by just giving you H, because at some point I have computed H actually the first step. So magnitude of H would be replacing A, but that's not what I've done. I don't think I need this stuff here. As just an extra step if you really want A, which I think is preferable to H, because it gives you a size type of information. Okay, so let's see what I've done here. There's several ways to get it, so I'm going to just tell you that A is H squared over mu 1 over 1 minus E squared. So these will be covered because you have everything. H, you computed it. E is given. This is coming from, for example, the following. The radius of perigee is H squared over mu 1 over 1 plus E. There will be a cosine of theta here, but at perigee I am a 0 theta. But I also remember that some point we computed this, right? So it's one of those million equations that you can find in the book. And so invert, just divide by 1 minus E, and that's what you get. So that's your step number 6 if you want. We're not done. So this in principle gives you the 6 orbital parameters that I have defined, starting from R and V as vectors. Do you see any particular problems with this type of representation? Now, if you remember other angles well enough, and you look at this sequence, you should be able to tell me right away where the problem is. Where this choice of orbital parameters, in particular these guys here, they start becoming an issue. We have to do something, an additional correction. Basically, the same way I've done those corrections there, I have to be careful about special cases. Any ideas?
Don't you have to do them in specific order for it to be accurate to the Euler angle?
Well, when you choose to represent the orientation of a rigid body in three-dimensional space using Euler angles, you choose the order you want to use. So I'm claiming here that it's a 3-1-3 sequence. It doesn't matter that I wrote them in this order, but again, I'm not explaining Euler angles today in details. We'll do it next time. But if I call it a 3-1-3 sequence, the sequence would be rotating about the z-axis by an angle big omega, then rotate about the line of nodes by I, and then about h of this quantity here. So yeah, I choose that that's the sequence. But each sequence, so this is a symmetric one, and by symmetric I mean that this is a 3 and this is a 3. There's also 3, 2, 1 sequences that are not symmetric. The symmetric sequences have a problem in certain cases. The asymmetric sequences have the similar problem in other cases. It's usually about, it's actually always about the second axis. No memories at all? They really haven't explained all the angles to you, huh? Really? Okay, I'll do it next time, step by step. But imagine what happens about all these quantities that I've defined if I, inclination is 0 or 180. Which of those things that I've defined just blows away, doesn't even exist anymore? If I have an equatorial orbit, it doesn't matter if it's with h pointing up, meaning going this way or you're going the other way, it doesn't matter. So 0 or 180. It doesn't matter if it's one of the two. Which ones of those doesn't make sense anymore? There is one intersection that goes away. Two planes that usually, you know, yeah, big omega is gone. Big omega is gone. Those two planes, equatorial plane and orbital plane, they were, you know, creating a pretty clear line. When you put them on top of each other, that line is gone. So that's your singularity. Again, I don't want to get into all the angles today because I want to do them from scratch, since they're usually an issue and I want to clarify that issue. But see, at I equals 0 or 180, you have a problem. One of those things doesn't exist anymore, right? That's, you know, it's kind of a problem. You can easily fix it. You just have to decide what to do. But basically, I would say that step 7, if you really want to do it that way, if I equals 0 or pi, if you like degrees, 0 degrees, 180, okay? You have to choose what to do. And the way that I do it, and it's, you know, the only one that really makes sense is, well, just say that the line of nodes, it's an abuse, it doesn't really exist, just call it x. You can choose whatever you want. What is the intersection? What is the line of intersections between two, or intersection between two planes? Any line. So if you really have to choose something so that you can still keep the other parameters that I have defined alive, the little omega, you have to choose a direction n. Because then, if you still have an n, you can still talk about an omega, right? Because if I take this plane and I just push it down in the equatorial plane, the orbit is now in the equatorial plane, yeah, this doesn't exist anymore. But I can still say that I'm going to count the angle from the x direction to E. I can still do that, right? Do you see that? So if you look at that from above, you would have, say that this is your x direction, and this is your y direction, and the orbit is actually happening in this plane. Well, you know, the orbit could be with the line of ups like this. So your E vector could be pointing this way, for example. This is perigee. I still want a way to express where that vector is pointing with angles. Well, if I call this n, I know it's an abuse because there is no intersection really, but you can do that. You can still call this little omega. Or if you don't like that, choose another direction. Choose this one. But what I'm saying, you have to decide and tell the user who's going to take your code what is your choice when the inclination is 0 or pi. So you still define an argument of perigee. In other words, you're still able to tell me where the eccentricity vector is pointing. Right? It's just a defect of all the angles. All the angles have a problem when they're symmetric sequences. We'll see it in details. When the second rotation is 0 or pi, the same happens here. When the second rotation is 90 degrees or 270. Same kind of problem. There's something else that disappears. They're called singularities. But so that's usually what we do. And I'm not done yet. there's one more thing that could collapse. What is it? There is an additional angle that kind of doesn't make sense, or I have to give it some meaning if something happens. Okay, we agree that if the inclination is 0 or pi, there's no big omega, it doesn't make sense anymore. I am forced to choose an alternative to the line of nodes. There's something else.
Yeah, if you have a circular orbit, then it should be anything.
Right.
So omega is.
Omega is, I don't know, doesn't exist. But remember that the only reason why we're talking about little omega or argument of perigee and we define this direction is that we have this line in the plane of the orbit from which we start counting what we call the true anomaly, right? So we have this theta, which is an alternative to time, to tell me where the satellite is on that track. Well, same here, you have to choose what you do. If you have a circle, what I would do is choose, and you just have to state that to whoever is going to use your software, for example. Choose, what do we call that? R, the R that you're given at time 0 as line of ups, even though it doesn't really exist. In other words, you start counting thetas from your initial position vector. Because the situation you're going to find is the following. You have a circle. You are given, again, you're given R and V at some time, right? And you know, there's no E here. Where do you start counting your theta? Wherever you want. You choose. So there's nothing wrong starting counting theta from the R that you were given. So you call these R0, that's your reference, and any other position will be counted from there. So, make sense? These are all coordinates. We're free to do whatever we want, as long as... There's a question?
E is a vector, right?
Yeah.
Component x, y, and z hat. So the eccentricity depends on a plane, right?
Depends on the shape of on the position and velocity.
And an orbit will always be in a plane.
Yeah.
It requires a combination of 2 or more coordinates.
Can you repeat the question?
Is how does so I get how x and y, how that's related to eccentricity. How does that relate to 3D? Does it mean you get an eccentricity in all 3 axes? Does that mean you can have any orbital plane that you want, inclined as much as you want in any direction in space, and still have 0 eccentricity. It means that the shape of the orbit is a circle. But it's still dependent on all 3.
It depends on your position and velocity. If these two are given to you in such a way that they're always, first of all, initial condition, they are normal to each other, that doesn't mean anything because you may be a perigee or apogee, right? But then you go here, this is the definition, it's really a definition. The eccentricity vector is a defined vector this way. If this goes to 0, if this difference here is 0, that means that your orbit will continue to have position and velocity at 90 degrees with respect to each other, and is a circle. We've proven that, you know, in those videos for the week I wasn't here, that basically shows you what happens when E equals 0. You can also look at it from the Keplerian solution for orbits. If this is what we have, this goes to 0, is a constant radius. But it's a vector defined that way, and if the track is a circle, it will collapse to 0. I don't know if that answers the question, more or less, probably. Does make sense? Does this make sense? It's up to you to define the coordinates, and it's up to you to compute them and resolve any special cases or ambiguities that you may have. Okay, so this is really what you do if you're given position and velocity to go to orbital parameters. The inverse, if you're given the orbital parameters and you want to compute expressions for R and V, we'll have to go through other angles, and I'll do it next time. But for now, because it does take time, you guys can absolutely start looking at what I called uncollected homework 3, where you're going to do both operations, but we can look at just half of it, where you take Cartesian coordinates for R and V, and you go to orbital parameters. It's just the same instructions, and this is as well posted on my website from last year. It's no surprises. The way you convert coordinates didn't change from last year, so why is this taking so long? Whenever this works. Do you have any questions in the meantime? About Wednesday? No questions? Oh, I think I posted, 2 things I posted on Canvas. One of you kindly shared a PDF that explains how you can extract from the UF app, if you use it in MATLAB that way, actual M files, because it's not the first time that people have problems with that. They develop code and then they can't really save the M file. So he shared the instructions with everybody. And then I felt I could add a little bit of clarification about what you need to do in exams and tests. That page where you sign your name and put your UFID is something you must have. It doesn't matter if you think it's silly, you have to have it. So I hope now it's clear that you have to have it. And then in terms of the homeworks, you need to understand you're 93, kind of, close to 100. Patrick's job and Caesar's job is not copy-pasting from PDFs or Word files or whatever you turn into MATLAB and try to see if stuff runs. And it's also not their job to figure out which functions are missing in what you turn in. It doesn't matter if you copy my functions from the website and you add those to your deliverables. That's a package that works, because these guys are not supposed to hunt for the functions that are missing, okay? So I hope that's clear. No one really, I mean, if people forgot them, they really just forgot them by mistake. But I hope that, I've had people in the past, and it usually happens that someone assumes, okay, yeah, this guy had the function on the website, I'm not going to add it. Well, no, you should add it. Because you can write it from scratch as well. I mean, you don't have to use my functions. Okay, so this does the following. First of all, this is data from last year. You can update this. You can remove this and change them. If you go on the website spaceflight.nasa.gov, you can, in this case, access at a given epoch the Cartesian coordinates for the International Space Station in meters and meters per second, and the corresponding semi-major axis, eccentricity. I think the maximum eccentricity that you would ever see for the ISS after it boosts to regain altitude is 0.004 maybe. It really doesn't go very high. It's a circular orbit. Inclination, this would be the WP is the argument of perigee. See, these are in the ranges that I told you. The right ascension of the ascending node is almost, it's more than 300 degrees, more than 180 for sure. TA, true anomaly. This is mean anomaly. It doesn't. The mean anomaly, we have defined that, right? Have we? Well, mean motion, I think, we have defined. But yeah, there's basically almost no difference here because it's a circular orbit. And I think these are, I don't know whether I'm using nautical miles for height of apogee and perigee. But forget about these last 3, really. These are the 6 that we have discussed. And so I'm asking you to go back and forth. What we've done today is go from these parameters to these 6. And what we'll do next time is vice versa. Notice that these guys, I believe they're using an ECI coordinate system defined in the 1950. Don't ask me why. But see, they're telling you what reference they're using. At least you know. You need to know. So there's no, I think, international, police that is asking people, that is forcing people to use a certain epoch for ECI, but you have to specify what that is. And so in the first half of this code, which is online, we go from this. I just copied the numbers, and I am doing it in kilometers here, so there's a 10 to the minus 3, these are in kilometers. And these are actually the other initial conditions that in uncollected homework 3 I am asking you to test. And they're just special cases that test your algorithm to see if it still works for special cases. For example, let's see, I believe this is an inclination of 90 degrees, because the velocity is 0, 0, actually, yeah, on the z-axis only. So play with these, they should give you special cases that we have discussed today. But that one up there is the most interesting one, is the International Space Station. Okay, so these should do exactly what we said. We start from h, compute its norm, do the arc cosine. Down here, everything I do in MATLAB that involves an arc cosine or an arc sine, something that should never see anything outside of 1, there's always this correction, I don't know if you remember, because otherwise you get complex numbers and the rest makes no sense. And so we get the inclination, let's see if it matches. In degrees, it's 51 degrees, 0.4113, and yeah, that's what we have. It's good to check with real data. At least you know that your stuff is working. Then this is the, let's see, oh, okay, yeah, special cases. If the inclination is 0 or pi, I am just forcing the line of node vector to be x. See that? Picking the x-axis. Otherwise, I compute the node line, as I said, the cross product of z. 0, 0, 1 is the z-axis, and h normalized. Do another arc cosine. This time we're computing the ren. That's in radians. If the node line is past pi, we fix that, and then finally convert to radians. 324, etc., etc., and that's this number up here. Okay. Yeah, we still have time to finish at least this sequence. Let's see, what else? What comes next? Eccentricity, it's pretty simple. Its norm, I think that's what we had, 0, 0, 21. And what are we doing here? Argument of perigee, the little omega. So all these ifs, etc., they should keep in mind what's going on. Now, what I'm doing here is I'm deciding what is the threshold to call the eccentricity 0. Because it's never going to actually be 0, but at some point you have to call it a circular orbit, and I just set it at 10 to the minus 3. You can change the threshold. So basically, this is all the operations we have discussed if the eccentricity is 0. I call less than 10 to the minus 3 0, otherwise the rest happens. Try to develop this from scratch yourself, even though this is posted. I don't know why this is taking so long now. What have I done? Pause? Oh my. Never had this happening before. Pausing. Okay. Did I hit pause? I just did, right? Anyways, believe me, if you finish this, you will get the same orbital parameters. It froze. It's not frozen? Okay, good. I don't know what I've done. Okay, argument of perigee in degrees is 94, whatever it was. Radius of apogee and perigee, so that I can compute the orbital period, and let's see, and A, same major axis, 677, that's what it is. I have noticed one thing over the course of time of using MATLAB. You don't get the same accuracy if you use degrees or radians sometimes. The functions work a little different. You may get different results, slightly different results. But so at the end of the day, if you run this whole thing, you should get the same values we have there. True anomaly also in degrees is 176. Let's see if it matches. I think it does. Here it is, except a few decimals. So, and this is what we do next time, the opposite. This involves rotation matrices and order angles definition, so we'll do that next time. Try try, well, I know you have a test on Wednesday, but try to do the first half of these as an exercise. Thanks.